Hey everyone! This is the second video on camera mirror lenses. In the previous video I discussed 3 different lenses that I bought second-hand online. The first one was a Vivitar 800mm lens that had some serious issues regarding sharpness. The second lens was a Sigma 600mm lens that was optically okay but had bad coatings inside. And the third lens was this Soligor 500mm mirror lens that also was suffering from significant fuzziness. Now in part 1 I looked mainly at image quality, but I also discussed how you can identify aberrations in the lens using interferometry. And in this second part I initially wanted to show you how I tried to solve the problems of the limited sharpness of both the Vivitar and the Soligor lens. But while making the video I found out that describing the process of modifying the Vivitar lens was just way too elaborate to include in this video, especially since our Chief Communication Officer Dr. Fullersheit asked for some airtime at the end of this video. So instead I will focus on the Soligor lens for now and leave the work on the Vivitar lens for another time. But what I will show you in this video is a somewhat different approach to measuring optical performance, and with a method that most people can basically do at home. So let's dive right in. As I showed in the last video, the Soligor 500mm mirror lens not only lacked good sharpness, it also displayed asymmetric bokeh when defocused, and this suggested that something was misaligned inside the lens. Opening the lens was done by removal of a total of 6 tiny screws and a ring, after which the threaded back of the lens was unlocked. However, the back could not be removed due to the fact that the baffle tube connected to it sticks through the main mirror and for some reason was designed to be bigger in diameter than the hole in the mirror. So I proceeded by opening the lens from the front side to get access to the baffle tube. After unscrewing a ring, the front aperture lens and secondary mirror could be taken out and the baffle tube could then be removed. And this then released the back plate from the lens housing and allowed access to the main mirror, which is still fixed in place with another ring. Initially, the biggest surprise for me was that both the primary mirror and the secondary mirror are second surface reflectors. So unlike what you find in most telescopes, which mostly contain first surface reflectors, here the reflective coating is on the back side of the optical glass, a bit like you find in a bathroom mirror actually. Now you might think that this is for coating durability, but in fact this is part of the optical design. So let me shortly explain how I think this works. If you use first surface reflectors like the ones found in telescopes, there is no easy way to avoid the use of aspherical surfaces like parabola and hyperbola in your optical design. And as I showed in the videos on the monolithic telescope, making good aspherics is very difficult and time consuming. So from the viewpoint of manufacturability and price, there is good reason to stick to using spherical surfaces only whenever possible. But why use a second surface reflector here? Well, you can actually mimic the properties of an aspherical mirror surface by using a combination of a refractive and a reflective spherical surface. And let me show you how in this very simplified example. Here you have a spherical first surface mirror with light of 550 nanometers coming from a point at infinity. And here you see the size of the spot in the focal plane. Now notice the scale, which is 1000 microns or 1 millimeter. So this focal spot is quite large, which is due to the spherical aberration introduced by the spherical reflective surface. Now let's add a second spherical refractive surface in front of the reflector and optimize its radius of curvature with respect to the spot size. And what you see is that by adding this additional refractive interface, we can create a much smaller spot. Again, notice the scale, which is now 10 microns, so a factor of 100 smaller than in the previous plot. Maybe you now think, well, if things are that simple, why don't we use this principle for every telescope instead of trying to make these difficult aspherics? Well, of course, there's also a downside to this approach. I mentioned that the situation I just showed is for 550 nanometers, so monochromatic green light. But look what happens if we were to use white light. Here you see what happened to the spot size of, for example, blue and red light in the same configuration. And while the green light is neatly focused, the other colors now have spots that are much larger. And this effect is caused by optical dispersion. So almost all glasses have a refractive index that varies with wavelength, and due to this property, different wavelengths refract differently after passing the first surface and on the way out. And eventually this leads to the focal points of the different colors to be located in different locations. So to avoid ending up with a large chromatic aberration, this effect has to be corrected for somehow. For example, by adding other optical components in the system that somehow introduce the exact opposite chromatic effect as the one created by this mirror. A bit like how the two elements of a doublet lens do this, where one element corrects for the chromatic error of the other one. So in our mirror lens system, the correction could be done in the front lens or by other optical components that are designed to minimize the chromatic effects. For example, the lens here at the end of the optical path, which is a concave cemented doublet, and it's also probably intended partly for this purpose. While disassembling the lens, I accidentally noticed something peculiar. The secondary mirror seemed to be slightly off-centered with respect to the front lens, actually a little over 1 millimeter when I measured it. So when I removed the mirror from the lens, it turned out that the hole in the front lens has very generous tolerances, allowing for plenty of room for the secondary to shift around. And with nothing really locking it in place other than friction, anything hitting the mechanism from the outside can potentially displace it quite easily. And an offset of the optical axis can easily be the cause of the asymmetric bokeh and the less than optimal image sharpness. So I decided at this point to put it back together and see if I could make it perform better by aligning the secondary exactly to the optical axis. I started out doing this by centering the secondary with respect to the edge of the front lens using a caliper, and I then temporarily placed it back with the secondary not tightly fastened, which allowed me to shift it around when using some pressure. Now, by looking straight into the lens, you can check if all the circular reflections look concentric, and if needed, you can apply small corrections to the position. However, the real test is in trying to create exactly symmetrical bokeh in the center of the image field, and this can be done by using a tiny high-intensity feature such as a reflection of the sun on an object. And deviations from the perfect alignment are especially visible when the amount of defocus is still small. By the way, the unevenness in the bokeh is caused by surface roughness, in this case mainly of the primary mirror surface. So with this test you can also quickly assess if your lens maybe suffers from a high surface roughness, which by the way is not really the case in this lens. So did this procedure improve the optical performance of the lens? Well, it may not be very obvious when you look at the full-size image, but when you zoom in on details, you can clearly see how sharpness has really improved. Now, visual comparison is of course one way to evaluate image quality improvement, but if you want to accurately describe the sharpness before and after improvement, it would be better if we had some objective way to measure it, especially if you want to compare it with other lenses. In the last video I used interferometry to measure wavefront aberrations in different lenses, but I must admit this is not a simple measurement to perform. I mean, it's nice if you want to know the exact nature of the wavefront aberrations to make corrections. However, it also requires special equipment and knowledge. But the main downside of this method is that we don't get the right information about image quality. For one, we only measure lens properties right on the optical axis, and on top of that, the measurement uses monochromatic light. In other words, this method does not give us any information about off-axis behavior or about chromatic errors. And image quality, as we perceive it in a photograph, is for an important part about these aspects. So this is why I decided to go down a different path here and show a method by which you can evaluate the complete image field, and on top of that is also accessible to anyone with a digital camera and a computer. The method was actually brought to my attention after the previous video by a comment from a guy named this guy. He mentioned some software called MTF-mapper. Now, I must admit I'd never heard of it, but as it turns out, the software can be downloaded for free, and I will add a link in the video description. As the name of the program suggests, it can map the MTF or Modulation Transfer Function in the image field. And for those of you whose knowledge on MTF is a bit rusty, let me quickly explain the main concepts again and then continue to how it's implemented in the software. As we have just seen, sharpness is all about how tiny details are reproduced by a lens. So say you have this pattern and you want to image it using a particular lens. The pattern consists of alternating line pairs that get increasingly narrower. In other words, the spatial frequency is increasing when we go from left to right. Now, the reproduction of the pattern in the image will never be 100% perfect due to the limitations that every lens has. So what you observe visually is that as the line pairs become narrower in the original pattern, more and more contrast is lost, which we experience as fuzziness. So, in the term Modulation Transfer Function, the word modulation refers to the black and white modulated spatial signal. The transfer refers to the reproduction process, and the function is a quantitative description of this process. The accuracy of the reproduction process depends on the type and the quality of the lens that is used, and the MTF plot shows how the contrast in the image depends on spatial frequency, which is often expressed in line pairs per unit of distance. For every lens, no matter how good, contrast gradually goes down with line pair density. Now, the power of an MTF plot is that it allows us to quantify the relationship between the two in a very detailed way. And we can then extract data from this function. For example, if we consider contrast loss of 50% the maximum acceptable value, you can take the MTF plot and find the corresponding number of line pairs per millimeter. And of course, the higher the number of line pairs, the higher we would grade the optical performance of a lens. So this allows us to objectively compare lens quality based on the maximum line pair density that can be resolved. And the software I've just referred to can do this kind of measurement in principle everywhere in the image field. Keep in mind that MTF is actually not about spatial frequency. In essence, it's about what happens in the signal in the transition at a high contrast edge. And so you don't need a pattern exactly like this to measure MTF, because you can extract all the information you need about the transfer process from just a single edge. Here is an example of a test pattern that is supplied with the MTF-mapper software. It just contains a pattern of blocks whose edges have a specific orientation, and the software looks at what happens to these edges in the image and can extract the modulation transfer function from each individual edge. And this allows it to calculate the MTF not only in the complete field, but also in a specific direction. The software assumes that the edges in the original pattern are pure step functions. The recorded image will contain a more gradual drop-off due to the limitations in the performance of the lens, and this gradient will extend over several pixels on the image sensor of a camera. So the software extracts a drop-off curve from the pixel information and converts it into a curve and then into an MTF plot. And depending on what your requirements are as an acceptable value for the loss of contrast, you can calculate the local lens resolution in line pairs per millimeter at each individual edge. The software can make different visualizations of the results and can even quantify the chromatic aberration over the image field. It does this in a similar way, but then by measuring the individual intensity profiles of the RGB channels. So to do actual measurements, I had a few of these test patterns printed out at a local print shop in high resolution and in a few different sizes. Now, the reason for printing different sizes is that lenses of course have different fields of view. So if you want to compare lens properties at the same object distance, you need different pattern sizes. I then glued these prints to a plate to make sure that they were flat, because it's vital that patterns are not curved or bended in any way when you photograph them. What's also very important is that the center of your pattern is exactly centered to the optical axis of the lens under test. And according to the manual of the software, this deviation should be smaller than 1 degree. So what I did to achieve this was add a small nail in the center of the pattern. I could then hang a reflective disc taken from a hard drive on this and then check whether the lens has the correct orientation by matching the reflection of the center of the lens with the center of the pattern. Now, the next steps are pretty straightforward. You can take a photo of the pattern with the best possible focus and in an uncompressed format like RAW. You don't want to use JPEG because the compression can seriously mess with the intensity profile at the contrast edges. And after you've set a few key parameters like the pixel pitch of the camera sensor, you can load this image into the MTF-mapper software. And that's basically all there is to it. All this thanks to Frans van den Bergh from South Africa, who put in all the effort to program this and make it available for download. I first tried this method on a standard 18 to 55mm Canon zoom lens, which I frequently use for making videos. I show these results here mainly to give you a frame of reference with respect to the number of line pairs that you can achieve with this sort of standard lens. I opened the lens aperture to the maximum setting and then took a few pictures of test patterns at 24mm and 55mm zoom settings. And here are some results. I won't go into all the stuff the software can show you, but just want to stick to presenting some line pair density data. In this plot you see how the MTF is distributed in the image over the horizontal direction. And it is clear that the lens is sharper in the center at this focal length. The resolution of this lens at 50% contrast loss was measured to be between 40 and 60 lines per millimeter, depending on the location. I also measured the properties of the lens at a 55mm focal length, and here the maximum line density is a bit lower, about 30 to 35 lines per millimeter, but it's also more evenly distributed. Let's now quickly take a look at the results of the tests on the Soligor lens and compare performance before and after correction. Here you see a measurement before the correction. The lens resolution that the software measures is about 8 lines per millimeter. I think though that it's probably quite a lot lower on average, because what you see is that the software has trouble measuring the MTF from a lot of edges in the image. Now if you go to the results of the corrected lens, this is not the case anymore and we get accurate measurements on almost every feature. For the line pair resolution I found a value between 17 and 20 lines per millimeter, depending on how much effort I put into collimation, but also into the MTF measurement itself. So yes, we observe a substantial increase in resolution by approximately a factor of 2.5. Now you might wonder, is 17 or even 20 line pairs per millimeter impressive for an optic with this focal length? And the answer is no, not by itself. If you compare the value with, for example, a modern telezoom lens like the one on the Nikon P1000, it's really not that impressive. The P1000 can deliver about 60 line pairs per millimeter at a comparable true focal distance, and this is more than 3 times higher than the value of the collimated Soligor. But to be honest, this is not a fair comparison at all, because the Soligor lens was designed for analog photography and has to deliver this resolution over an area of a full frame, so 24 by 36 millimeters. And the P1000 achieves its high resolution because it uses a ridiculously small chip, which measures only a little over 4 by 6 millimeters. In fact, it's almost 6 times smaller than the full frame in both directions. So yes, the lens of the P1000 is much sharper, but only within a very limited field. Okay, I want to end my part of the video here. I hope I gave you some new insights into optical testing and... oh, wait a minute. There is just one more thing. I regularly check the analytics of my videos, and what I've noticed is that the viewer population only contains a tiny fraction of female viewers, which led me to ask the following question to my daughter. So, what is it with women and optics?
Maybe it's just not sexy enough.
Sexy? I know somebody who can make anything look sexy. You want me to do what exactly?
Well, can you make optics a bit more funky or exciting?
Oh, yeah, sure, I can do that. Ha, no sweat. Okay, later.
Clear, don't overdo it.
Interesting. Let's see. It's 2022, and it's high time to shine some lights on optics. My name is Liam, I'm a funkoptician. I scan the room with my laser vision. You don't need a high power lens to see, I'll have my MTF on MTV. We can grind all through the night, my dear, until every surface is a perfect sphere. I can feel your fringes when we interfere, so let's transfer some modulation right here. The spread function pointing in your direction has an optical axis made for satisfaction. No spectacles needed for you to see, we're a perfect match chromatically. And dilation is what will occur when I focus on your aperture. So if you image me the way I image you, there's infinite conjugate things to do.